NanoHub U, online instruction.
So hello and welcome back. So now that we've developed our theory for the nanotransistor, it's time to take a look at experimental data and see what we can learn by applying that model to experimental data. So just to remind you very briefly, we're going to apply this virtual source transmission model that we've developed to real data. The transmission model that we've developed expresses the linear current. We can write it in terms of an apparent mobility. The apparent mobility is related to the transmission in the linear regime. The transmission in the linear regime is related to the mean free path and the length of the channel. The saturated current is related to the injection velocity. The injection velocity is related to the transmission in saturation and to the thermal velocity. The transmission is related to the mean free path, the same mean free path, we're assuming, as in the linear region, but the length is different. The length, script L, is a small fraction of the channel length. Okay, so that's our basic model. Now, these basic ideas have been implemented in a much more comprehensive model by the MIT group. We refer to that as the MVS model, MIT's virtual source model, and that model is summarized here. We begin by saying that the drain current is width times charge times average velocity at the virtual source. We have an empirical expression, or semi-empirical expression, that describes the inversion layer charge continuously from below threshold to above threshold. So some key parameters are the inversion capacitance, C inversion, M, the subthreshold slope parameter, KT over Q. There's a parameter alpha here, which is an empirical parameter, which accounts for the fact that the threshold voltage is really different in weak inversion and strong inversion, and that occurs because we can bend the bands a little more than 2 psi B in strong inversion. Okay, we account for Dibble, the fact that the drain voltage can lower the threshold voltage with a Dibble parameter, and then we write the average velocity. So charge, we just discussed the charge. Average velocity is written as a drain saturation function times the injection velocity. The drain saturation function is an empirical function that smoothly connects the linear current to the saturated current, and there's an empirical parameter in there, beta. And there's a drain saturation voltage, which is related to the injection velocity and the apparent mobility. All right, so the nice thing about this model is that there are only 10 really device-specific parameters here, and most of them have clear physical significance. There are a couple of empirical parameters, which once you're working in a particular technology, they get adjusted to that technology and they don't change much. But the capacitance, channel length, and the other parameters are parameters that have a clear physical meaning that we either input, like the channel length must be known, the gate capacitance must be known, or we extract. The key parameters that we're going to extract are the apparent mobility and the injection velocity, and the series resistance too. So the fixed series resistance of this device is also an important parameter that can be extracted. So my objective in this lecture is to illustrate how we can use this virtual source transmission model to analyze experimental data. And we will be looking briefly at silicon N MOSFETs and at 3.5 N-channel HEMTs. So the silicon devices that we'll be looking at are extremely thin SOI devices fabricated at IBM Research. You can find more details about the device itself and about the analysis that I'm going to briefly describe here in this reference. Just some key parameters. The silicon layer here is about 6 nanometers thick. The inversion capacitance is about 2 microfarads per centimeter squared. The effective mass, the appropriate effective mass, it's a little bit bigger due to quantum confinement, bigger than the bulk transverse effective mass of silicon, which is 0.19. The appropriate effective mass is about 0.22. If we plug in numbers for the unidirectional thermal velocity, we get 1.14 times 10 to the 7th centimeters per second. Now, if we measure the mobility on a long channel device, where the apparent mobility is the actual mobility, then we find a mobility that is about 350 centimeters squared per volt second. And that implies a mean free path that is about 16 nanometers long, about half this channel length. So we expect to be operating in the quasi-ballistic regime. Now, we will also be looking at 3,5 HIMPS. So the device structure is a little more complicated. It consists of a number of layers that are grown epitaxially on a substrate, the semi-insulating substrate. The key part is this indium arsenide channel. And that indium arsenide channel has a very high electron mobility. It has a very light effective mass and a very high mobility. That's why this transistor is called a high electron mobility transistor. That's what HIMP stands for. So just some key parameters from this particular device. The thickness of the channel is 5 nanometers. The inversion capacitance is about 1 microfarad per centimeter squared. The effective mass is very light. It's about 10 times lighter than that silicon example we just saw, about 0.022 times the electron rest mass. When we evaluate the unidirectional thermal velocity in this case, we get a value that is more than 3 times higher than what we computed for silicon, 3.62 times 10 to the 7th centimeters per second. And if we measure the mobility on a very long channel device where the apparent mobility is the actual mobility, we find an extremely high electron mobility, over 12,000 centimeters squared per volt second, which suggests a mean free path that is very long, about 153 nanometers. That is significantly longer than the 30 nanometer channel lengths that we're going to be looking at. So we expect this transistor to be operating very close to the ballistic limit. All right, so let's look at the silicon data first. Here's the actual measured output characteristics, and the solid line, the red lines here, are the MVS fit. So you can see that the MVS model does a good job of fitting these characteristics. The key parameters that we extract in doing this fitting are the apparent mobility and the injection velocity, and it's also useful to extract the series resistances as well. Okay, so let's see if we can make sense of some of this data. Let's look in the linear regime. Remember, in the linear regime, the key parameter in our transmission model was the transmission in the linear regime, T-lin. And we argued that theoretically it should be mean free path divided by mean free path plus channel length. What we extract is this apparent mobility. And the apparent mobility is a combination of the ballistic mobility and the real mobility. Okay? So if we divide the apparent mobility by the ballistic mobility and work out the result, this is our expression for the real mobility. It's related to the electron mean free path. And this is our expression for the ballistic mobility. It's related to the channel length. And if you work this out, almost all of the constants drop out, and we find that the ratio of the apparent mobility that we extract from the MVS fit to the ballistic mobility, which we know how to compute, is simply mean free path divided by mean free path plus channel length. That's the transmission. So we conclude that the transmission in the linear regime is just the ratio of the apparent mobility to the ballistic mobility. So it should be easy for us to estimate the transmission in the linear regime. We extracted an apparent mobility of 220. We can compute the ballistic mobility because we know the thermal velocity. The channel length is 30 nanometers. We get about 660 centimeters squared per volt second. We compute the ratio, and we conclude that the transmission in the linear regime is about 1/3. So this device is operating in the quasi-ballistic regime. It's not, transmission isn't close to 1, but it's pretty sizable, 1/3. So 1/3 of the electrons injected from the source make it across and exit through the channel, through the drain. Okay, so linear region transmission is something that it is easy to extract from the experimental data. Let's look in the saturation region and see if we can extract the saturation, the transmission in saturation. In this case, it's the mean free path divided by the mean free path plus this critical, the length of this critical bottleneck region. The injection velocity, we've seen is some fraction of the ballistic injection velocity or the thermal velocity, and the fraction is transmission divided by 2 minus transmission. So we can solve this equation for the transmission, and it's simply related to the thermal velocity, which we can compute, divided by the injection velocity, which we can extract from the MVS fit. So we have a simple way to estimate the transmission in saturation. We computed the thermal velocity from the effective mass of electrons in silicon. We extracted the injection velocity when we did the MVS fit. We put the numbers in, and we find a saturation transmission of 84%. Okay, so that analysis is easy to do. It's easy then to analyze experimental data and extract the transmission in the linear regime and extract the transmission in the saturated regime. And what we find when we do this analysis is, as expected, as we argued earlier, the transmission in the saturated regime, where the carriers are more energetic and are expected to do more scattering, undergo more scattering, the transmission in the saturated regime is distinctly higher than the transmission in the linear regime. Our analysis of the experimental data bears that out. And the physical argument, you'll recall, was that under low drain bias, the scattering matters in the entire length of the channel. So the critical length is the entire length of the channel, and the transmission is mean free path divided by mean free path plus the channel length. Under high bias, however, scattering only matters in the low field region near the beginning of the channel, and the transmission is mean free path divided by mean free path plus the length of that very short bottleneck region, which is why the transmission is higher in the saturated case. So the point is that the transmission in general is a function of the critical length, which is a function of the drain bias. All right, let's turn to the 3.5 data and take a look at it. Again, we can take the measured data. These are the measured output characteristics, the dots, and the MVS fit are the red lines. We see again that the MVS model produces a nice fit to the experimental data. We extract from this fit an apparent mobility of 1800. We extract an injection velocity of 3.5 times 10 to the 7th centimeters per second, and we also extract the series resistances at the source and the drain. Okay, so let's use our data, our extracted apparent mobility and injection velocity, the thermal velocity that we computed earlier, and see if we can do the same analysis that we did for the silicon MOSFET. So to extract the linear transmission, that's just the ratio of the apparent mobility to the ballistic mobility. The ballistic mobility we can compute. We have all of the parameters. Channel length is 30 nanometers. The thermal velocity is 3.62 times 10 to the 7th. We find a ballistic mobility that is a little over 2,000. So we can put numbers in our formula, and we find a transmission in the linear regime that is 86%, much closer to the ballistic limit than the silicon device was. In the saturated regime, we also have the numbers. We can easily compute a transmission in the saturated region, and we find in this case it's 98%. We are essentially operating at the ballistic limit in this 3.5 HEMT. So just quickly to compare our analysis of these two devices, what we find is that in the linear regime, we are in the quasi-ballistic regime in both cases, but we're much closer to the ballistic limit for the 3.5 HEMT than we are for the silicon device. In the saturated regime, even the silicon device is operating relatively close to the ballistic limit, but the 3.5 HEMT is essentially there. The injection velocity is a little less than 1 times 10 to the 7th in the silicon device. It is significantly higher than 10 to the 7th in the 3.5 device because of the light effective mass and the high thermal velocity. And all of this could have been expected because in the long channel devices, if we look at the mobilities, those mobilities imply a mean free path that is on the order of the channel length in the silicon case, but which is much higher than much longer than the channel length in the 3.5 case. So we would have expected the 3.5 transistor to operate very close to the ballistic limit and indeed it does. Okay, now what I want to do in the remainder of this lecture is just to look a little more carefully at an analysis in the linear and the saturated regime. So remember, in the linear regime, we extract this parameter, the apparent mobility. We know how the apparent mobility is related to the mean free path. We know how the ballistic mobility is related to the channel length. We can put these expressions together and we can derive an equation that looks like this. 1 over the apparent mobility is 1 over the scattering limited mobility plus the ratio of the mean free path over the scattering limited mobility times 1 over the channel length. What this says is that if the mean free path is independent of channel length, then if I plot 1 over the apparent mobility that I extract as a function of 1 over the channel length of the transistor, that will be a straight line, and the y-intercept will give me the actual scattering limited mobility, and the slope will give me the mean free path. Okay. So it's another way to get those two parameters. If we do that, here is an example of how that data looks. Indeed, it does fall on a straight line. From the intercept, we extract a mobility that is a little over 12,000, very close to the value that's measured on a long channel transistor. And if we extract from the slope, the mean free path, we find it's a little over 170 nanometers, again, close to what we estimated from the long channel results earlier on. So this is another way to estimate scattering limited mobility and mean free path in a short device. Okay, now let's look a little carefully. What if we plot the data and we find it's not on a straight line? That is likely due to the fact that the mean free path depends on channel length. So in that case, we can manipulate these equations and we end up with an expression that allows us to deduce the mean free path at any particular channel length if we know the apparent mobility at that channel length. So by doing that, I point out that in this case, we must know the thermal velocity. In the previous case, I didn't have to know the thermal velocity. In this case, I have to reliably know that thermal velocity. But if I do, I can extract the mean free path. And if we do that for the silicon ETSOI device, what we'll find is that for very short channel lengths, the mean free path drops a bit. Now, this is something that is sometimes seen in transistors, not in all transistors. And people are still trying to understand in detail what exactly is going on here. One possibility is that this has to do with so-called long-range Coulomb oscillations, setting up oscillations of the carriers in the heavily doped source and drain regions that become very important at short channel lengths. Another possibility is that it is related to various details of the processing that introduce more scattering near the edges of the channel that affect the short channel devices more than the longer channel devices. But it's something to be aware of. There is a possibility that the scattering limited mobility is actually different in a very short device than it is in a longer channel device. That wasn't the case in the 3.5 HEMT, but it seems to be the case in the silicon device. Now let's look carefully at a saturation region analysis. So in the saturation region, we know how the transmission is related to the mean free path and the critical length. We also know that the transmission is related to the injection velocity and the thermal velocity. We derived that a little earlier. That's how we estimated the transmission in the saturated regime. So we can solve these two equations and we can relate the injection velocity to the mean free path and to the length of the critical region. Now, if we assume that the length of the critical region is proportional to the length of the channel, now that's a little hard to justify rigorously, but it seems to work in practice rather well, and there's even some support from some simulations for that assumption as well. But if we make that assumption, we can test it later. Then we can rewrite this equation in this form. 1 over the injection velocity is 1 over the thermal velocity plus some parameters times the length of the channel. So if we plot 1 over injection velocity versus channel length, then we ought to be able to extract from the intercept of that plot the thermal velocity. And that's useful because sometimes it's not so clear what effective mass to use in these very thin channels that may be strained and may be undergoing quantum confinement. From the slope of the line, we can extract the length of this critical region. So that is also something that is very useful. Here is such a plot on the 3,5 HEMT data, and you can see that we get close to a straight line. From the intercept of that straight line, we deduce a thermal velocity that is very close to the value that we estimated from what we thought was the effective mass for the electrons in the indium arsenide. And from the slope of this line, we extract this parameter squiggle, which tells us that about the critical length of the bottleneck region under high drain bias is about 10% of the channel length. The channel length is 30 nanometers, so that means that that bottleneck region is about 3 nanometers long. So it is indeed very short, as we've been arguing. Okay, so just to summarize the analysis that we can do, we can easily do an analysis by fitting the MVS model to experimental data, and then we can quickly extract the transmission in the linear regime and the transmission in the saturated regime. We can do a little more careful analysis, and if the mean free path is independent of channel length, then we can plot 1 over the apparent mobility versus 1 over the channel length, and we can extract the mobility due to scattering and the mean free path from such a plot. If the mean free path is channel length dependent, then we can plot the data in a different way, and we can extract for any given channel length, we can extract the mean free path and apparent mobility at that channel length, and then we can extract the mean free path at that particular channel length. And finally, if the mean free path is independent of channel length, then a plot of 1 over injection velocity versus channel length will be a straight line, and from that we can extract the value of the thermal injection velocity, and we can extract the length of this critical bottleneck regime. So there's some very useful ways that we can analyze experimental data and extract some very important physical parameters. So just to summarize, this MVS transmission model provides us with a good way to extract important physical parameters from the measured characteristics of good transistors. Now, I'll just emphasize, we're discussing here good transistors. The MVS model and our transmission model is really a model of well-behaved transistors. In early stage development, many things can go wrong. There can be many non-idealities, and you wouldn't learn very much from trying to fit an MVS or transmission model to data like that. But when we have a well-behaved transistor, then we can learn a lot. And for those of you that are interested in more discussion about analyzing experimental data, I would encourage you to have a look at these 2 references. So, thank you.